Good morning, and thank you for joining us for our Misconceptions and Off-Grid webinar brought to you by AE Solar. Before we begin, if you're experiencing any technical difficulties, please notify me by typing your question in the questions section of your control panel on the right side of your screen and clicking send. We will have a Q&A session following the presentation. You are welcome to submit questions at any point throughout the presentation, and we will do our best to answer if time allows during, and if not, afterwards. There will be a brief survey that'll pop up in a new window immediately following the webinar. If you could take a couple minutes to complete that, we would appreciate it, and we'll email you a copy of the presentation for doing so. If there are no questions, and it looks like we are good in that area, I'd like to introduce our presenters today. It's AE Solar's very own Senior Manager of Product Management and Technical Sales, Josh Brister, and Brad Bassett, Senior Applications Engineer for AE Solar as well. So Josh, I'm going to pass the presentation over to you to get things kicked off, and thanks everyone for joining us.
Awesome. Well, thanks, Erin. Good morning, everybody, or I guess good afternoon if we've got anybody on the East Coast or further east than that. We have got a jam-packed presentation today, focusing on some common misconceptions that we see around the off-grid application, and thought this would be an interesting way to position all the material we've got. The off-grid webinars that we do are always among the highest attended and the most watched on our YouTube channel, so we feel like it's good information to share. And at this time around, we would kind of share it through the lens of, rather than just focusing on the best practices, focus on maybe the things that need correction or the things that are commonly misunderstood. So you guys know me. I like to start with an agenda slide. Let's take a look at that. Not going to be a lot of preamble today. Not going to be a lot of setup, just because we've got so much content to get through. So you got here a list of what we're going to cover. The first misconception really is, what does off-grid really mean? We'll walk through the solar production part of it, some racking misconceptions, of course, batteries and charge controllers, power electronics, and then finally some questions about loads. And we'll wrap it all up with some summary. And as Erin mentioned, we'll have some time for Q&A. So I said we've got a lot of content today, and I really meant it. So let's get kicked off here. All right, Brad, what's the first misconception you see when people talk to you about wanting to go off-grid?
Hello, this is Brad. Good morning, everyone. Well, the first thing is, you may get somebody say, I want to go off-grid, but what does off-grid really mean? To some people, it's just, I'm going to put some solar on my house. Some want to actually have, solar with storage for backup power, or some people want to go off-grid without a utility connection entirely, which is actually what we're going to cover today, is really off-grid without any utility connection at all. Having a utility connection changes things. Having no utility connection makes it a different aspect altogether. So what we're going to look at today is just sort of some questions that pop up often when people are talking about going off-grid.
Excellent. The first misconception here around the array and the sizing, Brad.
Yeah, so a common misconception is that you can size an off-grid system the same way you would a grid tie system, and by just simply going with a system, an array that's sized on an annual average production, which works fine for a grid tie system where you have unlimited storage on the grid and can get credits that you can use later when there's not as much sun. For an off-grid system, of course, you have to size it for the worst case time period. Normally, that would be for many locations, that would be particularly in the north, that would be in the winter, when you have the least sun and generally the most loads to power. Excuse me. For some southerly locations with a lot of air conditioning, it could be that the worst case time period is actually in the summer, which is actually a better fit for solar because there's generally more sun then also. And of course, the solar array has to be large enough to overcome all the inefficiencies and large enough to recharge the battery bank for use, when the sun is not shining.
Right. So the takeaway here is you can't use averages. You've got to plan for the worst case scenario, right?
Yep.
Yep. So walk us through this, Brad. You've got a chart here with kind of seasonal differences between production and loads.
Yeah. So this is sort of a typical printout from a sizing program that shows actually what this shows is potential solar production. And the blue is the loads, in this case, fairly steady loads. And the reason I say potential solar production is because once you have satisfied the loads with your solar and you have your battery fully charged, there's no place for that solar production to go, and you will not see that solar being converted into any usable form. So this actually, the actual production from the solar is actually going to be, these orange bars is only going to be just a little bit above the blue bars on a monthly average.
Mm-hmm. Yeah, great point.
So one of the questions or one of the misconceptions is that you size or you tilt your solar array at the same tilt as your latitude, or optimized for annual production, which actually is probably a little less than latitude. And in actuality, if you have a system where you're optimizing for winter, of course, it's very much better to tilt that array at a much steeper angle. Generally, what I'm looking at is in the southern part of the country, about 45-degree tilt, and in the northern parts of the country, about a 60-degree tilt is more optimal. The lower tilts can be done. It just means that particularly if you need to optimize for winter production, you're going to be putting on a lot more solar on in order to compensate for that loss of production from the lower tilt in the winter. And of course, another issue is snow. If you have a solar array up on a top of a 2-story house at a 4 and 12 pitch, when that's covered with snow, it might be hard to remove that snow. And when there's snow on a solar array, it has zero production. The sun does not get through it. So having a solar array in a place where you can easily, or at least can, get the snow off of it is good for an off-grid system, so that you don't have to have, be running your generator whenever there's snow on the solar array. If for some solar arrays, if they're steep enough, you may get the snow to fall off at some point. It depends what kind of snow you have. The snow we have around where I live in Olympia, Washington, looks like that picture. That's not mine, but that's what it looks like sometimes. And that snow does not come off until it gets warm.
Is that real wet snow?
Yep.
Yeah.
Yeah, and even at a 60-degree tilt like that, it still sticks on there pretty well.
I grew up in Northern California and was not aware until much later in life that there are different kinds of snow, in fact. Yeah, that's interesting. All righty, trackers, Brad. What do you see here?
Okay. The issue with trackers for an off-grid system is that, if you're optimizing for winter, a tracker doesn't really help much in the winter because the sun doesn't traverse that much sky in the winter. It only goes from, southeast to southwest, and, you're not really tracking very much. So it doesn't really help much. And then in the summer, spring, summer, fall, you've got more than enough solar power if you've optimized for winter, and the tracking doesn't really help there because you're charged early in the morning and you're not getting any solar production the rest of the day, or only enough to cover the loads that are running. The other issue, of course, is cost, and sometimes it's less expensive just to simply double the solar array on a fixed ground mount or a fixed roof mount than it is to pay for a tracker rack. And there may be there are occasionally circumstances where you do want production throughout the day, water pumping, maybe even air conditioning to some extent. But it's expensive, and tracking mounts do require good exposure to the east and west, of course, in order to take advantage of that tracking and be spaced far enough to prevent shading. And of course, they're not as reliable. You'll see a lot of trackers that are now fixed mounts, although they're hopefully getting better. Some of them are better than others. But a non-tracking mount is quite totally reliable.
Mm-hmm.
And with solar being as cheap as it is, it's the issue of the expense of the trackers sort of makes it less attractive. The cheaper the solar, the less attractive it is.
Yeah, I think, my kind of personal rule of thumb on this is that trackers made a lot more sense when, I guess, land was cheaper and modules were $4+ a watt. With module pricing where it is now, and knowing that a lot of people in off-grid applications are going to be constrained on how much space they've got that actually gets good sunlight, your money's probably better spent adding a little bit more array and leaving it at fixed tilt.
Yeah, and thinking that a tracker you could use less solar and it takes up less space doesn't really work, because you do have the issue of trackers shading each other, and so it actually does take just as much space as a lot more solar does.
Yeah. There's no free lunch, right, Brad? Charge controllers. What do we see here that people sometimes get wrong?
Well, the misconception is really that you're sizing the inverter to the size of the solar array, and in an off-grid system, the solar is charging the battery, so there really is no correlation at all between the size of the inverter and the size of the solar array. What there is a correlation with is the size of the charge controller, and so the capacity of the charge controller is determined by the size of the solar array, and also the battery voltage will have a fairly strong effect on that. We will be looking at that. Where you have a charge controller that's built into the inverter, such as in, say, a SolarArc, then you do, of course, have a correlation, but at least with the charge controller part of the inverter with that. So you do have to match the charge controllers to the solar array and not the inverter.
So actually, I heard a very elegant and simplistic way to explain an off-grid system in an unusual place. It was, of course, on a YouTube video about folks using solar and batteries on RVs and travel trailers. And this gentleman phrased it, I'm going to try to paraphrase in the following way, that their RV was not run on solar. It was run on batteries that happened to be charged by solar. So it really kind of reframed the, it reframed the discussion on sizing of the array, sizing of the inverter, and really put the onus of the system on the battery, which I think is what we're trying to convey here. That the array needs to be sized to the battery, which is kind of in turn sized to the cumulative loads. And the inverter is kind of secondary to that, we're sizing the inverter to maybe peak loads. But the pacing item, if you will, of the system is going to be the battery bank.
Right, and the inverter is just simply a load.
Mm-hmm. Yeah, kind of really reframes that whole scheme for me. Yeah.
Yep. Okay, so this is more a misconception that you'll see from do-it-yourselfers and people that come from maybe from an RV background, where a lot of people will just simply think that, well, a 12-volt battery bank is an off-grid system, or an off-grid system is a 12-volt battery bank. In reality, most systems that are larger than an RV or even RV-sized systems, 12 volts battery bank is really sort of obsolete at this point. Charge controllers have an output capacity. That's how they're rated in amps, and they will, of course, have the same current no matter what the battery voltage is. And you can see I've got a few numbers down here, and you can see that the watts that I end up with as a sum here, as a solution, is approximately the size of solar that you can handle with a 60 amp charge controller. So 12 volts times 60 is 720 watts. And if in actuality, you've got some inefficiencies, and the solar array nameplate is going to be higher than the actual output. So it's actually going to be higher than these. But you can see that for each doubling in battery bank voltage, you double the capacity of the charge controller. And so that really makes it considerably more economical to go with a higher battery voltage. The other note that I have in here is that the charge controllers that we use now are MPPT charge controllers, and they will take the voltage from the solar array and reduce that down to the voltage that the battery needs to be charged with. And in the process of doing that, will raise the current so that it charges the battery at a higher rate. The older style PWM type charge controllers that were the only type we had until almost 2000, somewhere in the 1990s, simply lets the solar array being connected to the battery directly, and just simply limits the voltage when it gets high enough. But that won't work with the 60 cell series modules that became pretty much ubiquitous, in the late 1990s or 2000s. And using one of those charge controllers with the modern solar modules will simply cause about half the production that you could possibly have from that solar array. And a lot of the charge controllers now actually will take even higher voltage input, and so you can reduce your wire size and increase your string length and the like. Mm-hmm. So you don't want to use one of those cheap or inexpensive, even if it's a good one, an inexpensive PWM type charge controller when you're using any of the modern type solar modules.
Yeah, so a couple of developments here that have really kind of changed the game, I think, and that's that MPPT charge controllers are, obviously readily available in a variety of sizes. They're pretty darn affordable when you think about what they can do. That allows you to run kind of standard modules at a higher array voltage. Question for you, Brad. Do you think most people get fixated maybe on the 12 volt system size because they feel that they've got 12 volt loads and that's the way to run it most efficiently, or because they've got 12 volt batteries, or how do you think people get to this point?
Well, both of those. In the early days of off-grid, people used RV appliances a lot because the inverters weren't very good. And of course, the RV appliances are all 12 volts. So certainly that was an early basis for that direction. Mm-hmm. And but as inverters got better and better, people used less and less 12 volt appliances. The RV appliances were not always all that great, and they were expensive. And now that the inverters are more efficient, and there are more higher efficiency 120 volt appliances also, you can actually do pretty well by going to just all AC in the house rather than trying to do DC loads. Yeah. And if you have a small DC load, a radio or something, then you can use either a DC-DC converter from your battery voltage down to that voltage, or you use an AC. If you've got your inverter going all the time anyway, just use a wall transformer. not very efficient, but if it's a small enough load, it's usually not a problem.
Oddly enough, well, not oddly enough, but one thing that definitely hasn't gotten cheaper in solar is wire. And you kind of alluded to this, that there's a lot of savings to be had in moving from 12 to 24 to 48 volts just on copper alone.
Yeah, and particularly high voltage input on the charge controllers can really make a big difference if you have some distance between the solar array and the power system.
Mm-hmm. Great points. What do you see around the inverters themselves, Brad?
Well, inverters in an off-grid system become much less smart, much dumber pieces of equipment. They don't really need to have all the smarts that some inverters have. Basically, it is simply converting your battery DC to AC to use for the loads. And of course, here again, we have the misconception that the inverter is sized for the solar array, but in actually in an off-grid system, it's really only sized for the loads that are placed on it, and not just the biggest or largest load, but all the loads that are expected to be placed on it at one time. Now, that does mean that a savvy user can control what loads they run when and keep the size of the inverter a little smaller, so it'll stay a little more efficient or be a little less expensive. So there are some battery inverters that can be used for grid tie, like the Schneider XW or the Outback Radian, Solarc. But most of them are just simply a converter that convert from DC to AC. And those inverters that I just mentioned, particularly the older style, Schneider XW and Radians, were actually based on a design made for off-grid use. They just discovered that they could use them for grid tie at one point many years ago. And these inverters have, or at least some of them, a lot of them have large transformers in them, and they have large power electronics in them, which can produce a bit of noise, both physical noise and electrical noise and magnetic noise, radio noise. So you do need to be aware of that. You don't want to mount somebody's inverter, on the other side of the wall from where they're sleeping or doing something that requires quiet, because they can be fairly noisy. And another little tidbit is that some of these larger inverters with big transformers can produce quite a bit of AM radio interference, and to the point that they're probably a little better now, but in years past, you could pretty much count on an inverter like this to completely obliterate any AM radio reception. I don't know if anybody listens to AM radio anymore, but it was an issue, or had been an issue. One of the ways to reduce that is to take the battery cables between the battery and the inverter and keep them as close together as possible between the two. Ideally, they would be twisted pair, but that's a little bit impractical with 2-aught and 4-aught cable. But if you just simply keep them together, that does help reduce that somewhat.
That's all interesting information, Brad. This slide's a little painful for me, having kind of I won't say grown up, but started my solar career at an inverter manufacturer. We just always felt like the inverter was the center of the universe when it came to the system, and I think it's certainly an important piece, but obviously not the most critical factor when it comes to sizing and design. A question here around where you would want to install the inverter or the inverter charger. Are most of these still NEMA 1 construction?
Yes. Mm-hmm.
Yeah. So you're going to want to, kind of a cool, dry place for these, not on the outside of the garage, I would think.
Not outdoors. No.
Yeah.
And not in the sun either, of course.
Yeah. All right. Batteries. So there's got to be a ton of misconceptions around batteries, right? Right, Brad?
Well, yeah, probably is. one is just the question, can you just size the battery so that you have sun during the day and you just need the batteries to get you through the night, which is not quite right. Yes, it does need to get you through the night, but it also needs to get you through multiple cloudy days. More of an issue in some places than others, but I don't think there's any place where it doesn't get cloudy for at least a few days at a time. And also you need to be able to, that battery bank needs to be big enough so that it can absorb the peak solar production in the middle of the day, or even the inverter capacity that's charging it. So it needs to be a little bit larger than that. It used to be that we'd make them considerably larger than that, but that's now the most expensive part of the system. So people tend to want to try to keep that to a minimum. And a battery bank that's too small, will simply lead to more use of a backup generator, which is polluting and expensive. And of course, that battery bank will also be discharged much more heavily, and that will reduce its lifetime also, particularly with lead type batteries.
Yeah, there's a couple things I've kind of picked up over the years around batteries, and the first of them is, you probably heard it, that batteries don't die, they're killed, which certainly resonated with me. The the other is not so much a saying as kind of a dialogue, and that's that when we would publish a new inverter manual, there would be a recommended minimum battery capacity of, say, 400 amp hours. And like clockwork, the first 40 calls to tech support would be, hey, can I use 100 amp hours? Can I use 200 amp hours? And the answer was always, well, I don't recommend it, but you're welcome to try. You're not going to like the results though, because you're going to work those 100 amp hours so hard that you're going to be replacing them every 9 months. And I think it's easy to focus on the upfront cost of a system because, hey, these aren't cheap, they're not free. But really the thing to think about is, do you want to replace that bank every 2 to 3 years, or do you want to oversize it and take care of it and have it last for 10?
Yeah, and the other issue is that inverters, particularly if you have a larger inverter, sort of work much better if they have a little bit larger reservoir to work from. They don't end up with as many transients, trying to power a larger load from a smaller battery and the like. At least that's what I've run into, having tried this myself.
Yeah.
With too small a battery bank.
Yeah, we I tend to try to explain things electrical through the lens of water, because people tend to understand water a little better, and maybe just because it's visible. And if you've got a huge pump, which is kind of analogous to an inverter, and you're trying to run it off of a reservoir the size of a kiddie pool, you're not going to be able to run it for very long, and there's going to be a lot of perturbations and air that gets sucked in, and it's you're always better running a large pump like that off of a larger reservoir, which is kind of the best way I've got to explain that phenomenon. So again, I think the thing that we have to coach people on is, we size the battery bank to multiple days of autonomy, ideally. Also taking into account, how many charge amps and discharge amps are you going to have from the system. And yeah, if you've got a small battery bank and you're dumping a ton of current into it, or you're pulling a ton of current out, it's not going to last very long, and you're not going to have good performance. So keep hammering that point home.
Yep, and keep in mind also that if a battery is cold, it's not going to have as much capacity and not be able to supply as much power to the inverter. So a bigger battery helps there also. Oh, I went the wrong way or something here. There we go. Installing a very large battery bank will cause problems. Well, if it's large enough, yes. And it also depends on what kind of battery it is. It's rare for a battery bank to be too large because they cost so much now. It's not very often that I run into somebody that puts in a battery bank that's too large. But if it's a flooded battery bank, flooded lead battery, they do require a certain amount of push current pumped into them to really operate well. And if you don't have enough solar, or you don't have a large enough generator to adequately charge it, it will not get fully charged, and then it will sulfate, and it will reduce its life pretty substantially. And the other issue is that, particularly with flooded batteries, is that they do have a fairly high self-discharge, which means that they're going to take a certain amount of energy just to keep them steady or keep them charged. And that can be fairly substantial with a flooded battery. So if your battery is too bit large, it's going to be as much of a load as your entire house load could be, potentially. So that's another reason not to oversize a battery, particularly a flooded lead battery. Sealed AGM gel lead batteries have a different construction, different alloy material in their plates, and tend to be much less of an issue with that. They're much more efficient, and you can recharge them with a small current and get them up to a full state of charge. Lithium batteries, same way. They're quite efficient, so you can get them up to a full state of charge with a smaller system. So oversizing those is generally not as much of an issue unless you really overdo it.
Mm-hmm. Yeah, I guess I hadn't thought about from the perspective of lead acid, what the self discharge and the minimum amps you'll need to get a full 3-stage charge to them. Good point. So I guess the takeaway here is not, it's kind of the Goldilocks approach, right? Not too small, not too big, but what's the right capacity given the system you're going to be using?
Yeah.
Okay. I think this is probably the one that I see the most, just in the questions that come through me around, hey, I've got this equipment or this battery, and I just need to replace one, and kind of the mixing and matching.
Yeah. This is sort of similar to one that we already went through. Where you think you just want a 12-volt battery bank, but it also applies to, do you just use 12-volt batteries, even if you put them in series to work at higher voltages? But most residential inverters are now 48 volts. There's still some 24-volt systems around, mostly older ones that are looking at retrofitting. But 48 volt is really sort of the standard voltage now for a battery bank on an off-grid system. And just to give an example, if you've got a 3,000 watt 12-volt inverter at full power, it's going to be drawing 250 amps. If you have just a single string of lead batteries, sort of your standard 100 amp hour or 200 amp hour battery with the lead posts on it, 250 amps is enough to almost melt those posts. And if you start pulling some surge power out of it, you're going to have some pretty serious issues with your battery bank being overheated. On the other hand, a 9,000 watt 48 volt inverter is only drawing 188 amps, and that's 3 times the size and drawing less current. So it really pays to use a higher voltage battery bank.
So if 48 is better than 12, then 240 or 350 has got to be better than that, right?
Yeah, well, theoretically, a higher voltage battery bank would be better. Smaller wire, less current, more efficient. The problem is that it gets to be a little bit of a hazard, and the code has actually restricted residential systems to 48 volts. Actually, I think it's 48 volts nominal, So, it actually can get up to 60 volts, but they're keeping it at that voltage. Commercial and industrial systems can go with the higher voltage battery banks. And they also require segmenting disconnects and certain grounding issues, all sorts of stuff. So for the time being, for residential systems, we're looking at 48-volt battery banks, and that's why that's become a standard, because it is the highest. Now, there are currently batteries, and actually they're called energy storage systems, ESSs, that meet the UL 9540 standard, and these are the grid tie systems that you see, the Solar Edge, LG, the Generac type systems, and they have also are using a different type of lithium battery, and they're all very well integrated. They have solid communications between the inverter and the battery to make sure that nothing goes out of spec, and they don't have any user accessible parts. It's all engineered as a system. None of those types of systems with the lithium NMC batteries, at least that we carry, are suitable or approved for off-grid use.
Mm-hmm.
This may change, but at the current time, all those companies making those types of systems are really orienting their market towards the grid connected systems.
Mm-hmm. Yeah, kind of two different sets of products at this point.
Yeah, but it's really two different markets.
Mm-hmm. I'm not sure how to lead into this one, Brad.
Well,
what
what I see happening a lot is, I mean, I describe, the difference between parallel and series. You can read about that if you don't already have that in mind. But what I see a lot is people saying, well, I've got a great deal on these 12-volt RV batteries, and I'm putting in a bigger system, so I'll just put in lots of these 12-volt batteries. I've seen systems with 48, little 12-volt RV batteries in it or more. Actually, I've seen some with 96 batteries in it. And you put them in series, you get 48 volts, you got 4 in series, but then people put lots and lots of parallel strings together to get their capacity up, to what they want. And with the lead batteries, it just doesn't work very well. And this has just come from experience, over the years. Even before solar was even around, this was still known, back from the early 1900s, actually, where if you put too many parallel strings, the cells get imbalanced to each other. And the more imbalance there is, the more some get overcharged and the more some get undercharged, and they're both damaged and have premature failure. So the rule of thumb is that with a lead battery, because they don't have a battery management system to do this balancing, you limit to 3 parallel strings. And one string is actually ideal. 2 strings is good, especially if you want some redundancy. If you have a bad cell, you still have half your battery bank. 3 parallel strings is okay most of the time. With flooded batteries, it can be a little bit of a problem. With AGM and gel batteries, it's not quite as much of a problem. Sometimes for just pure backup, UPS systems, you can go more. But for an off-grid system where you're cycling the batteries daily, 3 parallel strings really should be the limit.
Mm. So I'm a developing RVer, and I guess one of the first things I looked into was, the battery that came with the RV is just kind of a standard off the shelf, I don't know, Group 65 or something, 12-volt battery. And my first thought was, well, I'm probably going to need a little more capacity here if I want to, go boondock somewhere or camp somewhere without hookups. So started looking into replacing that with either two 6-volt cells in series or 2 12 volts in parallel. And the 12 volts are almost always cheaper, but the prevailing wisdom among the RV crowd is just that the onboard electronics are not sophisticated enough, and the wiring is usually not good enough to have 2 parallel strings. and that's almost always recommended to use the 6-volt cells.
Yeah, well, the common 6-volt battery for those would be a golf cart battery, which is usually often quite economical battery. There's just a ton of those made, and so they have a pretty good price on them.
Mm-hmm.
So it's sort of the opposite with lithium batteries. Lithium
Mm-hmm.
batteries come with a battery management system, a BMS, that keeps the cells within the battery balanced. And even the better battery systems actually come with multiple batteries that interconnect each other with their battery management system, so that they're all balancing themselves all throughout the entire battery bank. And most of the lithium batteries made for residential use or larger systems are made to work at the voltage that each unit is made for. So if you have a 48-volt inverter, you buy 48-volt lithium batteries. And or a 24-volt inverter, you buy a 24-volt lithium batteries. And then to get more capacity, you put them in parallel. And because they have the ability to balance themselves, you can put lots and lots of them in parallel. The Discover battery shown here can easily have 20 batteries all in parallel. And they all have interconnected communications so that they can all balance each other out. And some of them can even go, custom systems with, megawatts. And look at electric cars that have little teeny cells, thousands of them all in series and parallel. And one thing I sort of came up with here is that I recently looked at or tried to troubleshoot a system that somebody had put in locally, and he had bought 12-volt lithium RV batteries. And each battery had its own BMS built into it. But he was putting 4 of these in series for 48 volts, and they did not communicate between them. Each one only communicated within itself. And that system was so imbalanced after a few days of use that he would have to go out in the middle of the night and remove each battery, charge it separately at 12 volts until it was charged, and then put them back in service. He was getting a little tired of that. So you really want to, for a good functional residential system, you really want to use the lithium batteries that are at the voltage that you're utilizing in the inverter, and not putting them in series.
Yeah, I remember when we launched the Discover AES line, we worked with the rep and we're reading through the data sheets and literature, and honestly, I thought the 20 was a typo. Having come from a lead acid background like most of us, I just didn't. I had a hard time comprehending how the system would compensate for so many strings in parallel, or not even strings, but how many batteries in parallel, given that they would all see slightly different charge currents. And the short answer is a good BMS will take care of that, and will charge each battery independently. To hear that story about the lithium batteries in series, boy, I'm trying to understand what the BMS on each one of those would even try to accomplish.
Yeah. Well, and the 20 parallel limit on the AES battery is because of the communication system. It's not the battery itself. It's just that their communication system has 20 addresses in it or something like that. The other thing that I didn't put in here is that theoretically or commonly thought is that you can run the lithium battery at any state of charge, between 0 or just above 0 to almost 100%. And that's true to a large extent in that it won't damage the battery to do that. But the balancing in these batteries actually does happen mostly when they are fully charged. And so to really get them balanced, you really do have to get them up to a really full state of charge every so often, every few weeks or something. It's not anywhere near as critical as it is with a lead battery, but it really does work better if you use these, between 0 or 10% and 20 or 30% long enough, eventually they're going to become imbalanced, and they really do like to have a full charge and held at a full charge for a little while. It only takes 2 hours to charge, or 1 or 2 hours to charge these from empty to full anyway, so it doesn't take long. But it's good to get them fully charged every now and then so that they have a chance to balance the cells in there.
That's a great point. I've not thought about before. Okay. Learn something new every day, Brad. What do you see here when people try to retrofit to older systems?
Well, this is one I see people asking about a lot. Can I buy a smaller battery bank and then add to it later? Because you can add solar later, you can add inverters later, you can add loads later, but can you add more battery capacity later? And the problem is that with lead batteries you really can't, because you end up with an imbalance between old and new batteries, and some of them get overcharged, some of them get undercharged. It's a similar situation to having too many parallel strings, but worse. And so you really can't mix batteries, and you can't have old and new batteries, and so really you have to buy your battery bank, and that's your battery bank until you scrap it or sell it, and put in a new battery bank with lead in anyway. Lithium batteries are a little different. The manufacturers do not recommend that you mix and match. Well, certainly you wouldn't want to mix different kinds of batteries because your communications aren't going to match, and that would be a problem for sure. And even different size of the same model, even if they communicate to each other, is not recommended. You can try it, and I'd be curious to see how it works. But just within a certain amount of time, months or maybe a year or two, you could certainly add the same model of battery to the battery bank and get more capacity. And each battery will do its own balancing. The batteries are balanced to each other, and they will each contribute what they can to the capacity of the system. It's not ideal, but it's certainly something that can be done. If you don't have the budget to buy the entire battery bank up front, maybe 6 months down the road, you can add to it to get more of the capacity that you need.
So for the customer, or the guy or gal that says, "Hey, I've got a system, it works great. I need to add another. I've got more loads now. I need to add more battery capacity." What would we typically tell that customer?
Add more solar. And you'll just have to hammer the battery bank you have. And you'll just have to cycle it harder, and deal with it until such point as it gets to be bad enough that you either have to replace the battery bank anyway, or you get too tired of having too small a battery bank and replace it. But at that point, you really just have to replace the battery bank.
Really puts the kind of reminds us of this puts the onus on the upfront calculation and system design around what are your loads likely to be for the next 3 to 5 years.
Yeah, and don't undersize it, especially if you think you might have to have a larger system down the road a little bit.
Loads. I think that's what that's the end game here. But what kind of misconceptions do you see around loads and what people are trying to run?
Well, it's like I've got this house. I've either been connected to the grid and no longer want to be connected to the grid, or I've been running it on a generator for years and I want to go off grid with solar. I just want a solar system that powers the whole thing, the whole house, just like it is. And you can do that, but if you have a fairly inefficient house, it's going to cost a lot. So it just sort of depends on how much money you want to spend on it. You're buying your power that you're going to be using for the next few years all up front. Not the fuel, but all the equipment. And so being more efficient pays off. This was really, really critical back when solar was very, very expensive. It's not quite as critical now, but it certainly still has an effect. And so things that use a lot of electricity, particularly a lot of electricity for a long time, because that's really what the watts are, is power over time. It just makes for a much larger system. And of course, the main culprits there are space heating, water heating, clothes dryers, and electric ovens. Now, if you don't use them for very much time, clothes dryer, you only use it for an hour, most people a day or every few days. Electric ovens, sometimes people only use them occasionally. Those are not really bad, but putting in an electric resistance water heater would likely be a huge hit on your load profile. And of course, electric space heating would be just a huge, it would be a monstrous system to power that directly. So it's, more and more solar is cheap enough that people want to do, a whole all electric house. Back in the day, everything used to be propane this, propane that, but we're trying to get away from that now, because propane is fossil fuel. And so for heating a house, really, you come up with heat pumps is really the final solution. And of course, it's still a lot of energy to heat a house, even if it's doing it considerably more efficiently. So it's if you have the chance, it certainly pays to make your house more energy efficient, either retrofit or new construction. It really will make a big difference in the size of the solar system that you need. And it's not necessarily just the solar panels, it's the battery bank. The battery bank is going to be probably 50% of the cost of the materials for the off-grid system. And so that's really where you really need to conserve in order to keep the cost of the battery bank down.
Yeah, that makes sense. It's not, not sexy. It's not exciting. It's not, equipment that we really get pumped up about. But yeah, envelope, insulation, weatherizing, just you can't overstate how important that is to a good off-grid system design.
Yeah, there's a couple of other things. Well, of course, there's people up here in the North Woods heat their house with wood, which is, you can argue about whether that's good or not. But also another thing that can be used to good effect is solar hot water, good old solar hot water. Flat plate collector, heating up your water. Our water heater basically doesn't turn on between June and October, and I'm in the cloudiest part of the country.
Yeah.
In a lot of parts of the country, you have solar hot water. Your water heater is probably just almost never going to turn on. And it just sits there and it does its thing and heats up the water. It's a great way to go to get hot water.
What's old is new again, right, Brad?
I'm sorry, what?
What's old is new again.
Yep.
So, to kind of summarize here, it's how would you tee this up, Brad, on kind of the most common misconceptions and maybe what the big picture looks like?
Well, when somebody wants to go off grid, there are justifications for doing so. If the utility simply is not available, and that's becoming more and more common, or if it's just simply going to be way too expensive to get power to the site where you want to build your house, those are definitely justifications for going off grid. You are buying your power up front, or at least the equipment to utilize the solar power up front for this, so it is going to be more expensive up front. Solar is not necessarily, more expensive than grid power at this point. It's getting closer, and actually on the utility scale, I think it's actually cheaper. But where the cost really comes in is when you have to run an engine generator to get your power. Engine generators, you're just talking about a small, at most, 20 kilowatt probably generator, and at full power, where that generator is running most efficiently, you're still going to be looking at something like 50 cents a kilowatt hour for your power. And most houses are not running a generator at full power. They size the generator for peak loads. And so most of the time, you're probably going to be looking at more like $1 a kilowatt hour for your power from a generator, which is way higher than solar or grid power. And so you have to look at this in the long run. You know, is it cheaper to buy more solar, more battery, or to rely on a generator for your power? And this is really an issue up here in the Northwest, where there's just not much sun in the winter. So going off grid really is, expensive because you're running your generator a lot.
Mhm.
And then you've got maintenance and replacement costs for generators too. If you're running a generator a lot, they don't last a whole long time. Every few years you may be rebuilding it or replacing it. Yep. So that adds to that cost above and beyond the dollar a kilowatt hour. So yep, it's not something you want to do if you don't have to, or if there's not a pretty good justification for it.
Yeah. And as you said, they're noisy and there's a lot of emissions there, which, certainly something I'm cognizant of.
Well, yeah, you'll see a lot of people go off grid. They'll minimize their solar system size, and so I can just make up the difference in the generator. And 2 months later, they're like, okay, how do I expand my solar system? Because I'm really tired of running this generator.
Mm-hmm.
Yep. I mean, there's things you can do to make it, a little bit more acceptable. I knew somebody that had a generator. They'd put it down in a vault underground, as far from the house as possible, and you could barely hear it from the house except when it was really quiet out. Things like that. But yeah, running a generator is pretty unpleasant.
Yeah.
And then there's some people who say, well, I want to do my thing for the environment by going off grid. Well, that
Mm-hmm.
is what is a non sequitur is the right word? That doesn't really follow. Going off grid means you're going to use a lot more solar panels. It means you're going to use a larger battery bank. All these things have, an environmental footprint. And, solar panels are of course, a very good choice because the energy used to manufacture them is easily produced or replaced by the solar panels in a very short time. Batteries a little less so, of course. But running an engine generator for off-grid, of course, relative to the amount of energy you're getting is an environmental disaster. It's huge pollution, huge amount of CO2 in relation to the energy that you're producing. So going off-grid, if you have grid available, is more of a political choice rather than an economic or environmental choice. If the grid is not available, of course, that's not an issue. But if the grid is available, going off grid is, you'd want to think twice about it.
Yeah. And that's, I mean, that certainly becomes a bit of a rabbit hole when you start talking to people about how clean or dirty, relatively speaking, the grid actually is. And the answer is, well, it depends. Depends where you are, depends what time of year and what time of day you're talking about. But most of the states that we're in and that our customers are in have some form of renewable portfolio standards. And I think it's a very safe assumption to say grid power on average is cleaner than generator power.
I don't think you can even say on average. I would say even the worst coal-powered power plant in relation to the amount of electricity produced is probably less polluting than a generator.
Yeah. Well said, Brad. Which, as there was some news this week around electric F-150s and kind of setting the internet abuzz about, how, you hear a lot of, I guess, red herring arguments around, well, EVs aren't clean because, the grid's powered by coal. Well, No, predominantly the grid's powered by renewables and natural gas, all of which is probably better than, a V8 engine at 17 miles per gallon. But I digress. We are at the top of the hour here, and we've got some time for some questions and answers if any of the former have come in. Aaron, do we have any good questions from the audience today?
Not as of right now.
Wow.
Yeah.
I guess we were very thorough, Brad.
I was just gonna say that. I think you didn't, maybe you were so thorough that nobody had any questions. Oh, I see one coming in.
Okay.
Okay.
Yeah. It just takes a moment for people to catch up a little bit.
Give me 1 second here. I'm trying to expand the question box. Are you able to see that, Josh, the question box?
I am not, no.
Okay. Okay. Thanks for your patience here, guys. Trying to, the question box went and disappeared. I'm trying to find it. I am not having any luck finding the question box, guys.
Oh, okay. Well, we can certainly address that one offline once we find it. Just want to send a couple reminders your way that there's a survey that'll follow here, and we love hearing your feedback on not just how we did on this one, but what kinds of topics you guys want to hear about in the future. Very helpful for us. And Aaron, once those folks complete the survey, they will get a copy of the presentation as well, right?
That is correct. And actually, we are in luck. I was able to find the questions panel. So we've got a couple, we've got about 3 questions. Do we have a couple minutes to answer those?
Yeah, I got some time.
Perfect. So we have one from Raj Patel. What about permitting? Is it good to have a full set of plans? And then he also asked, what are the most common warranty claims?
Well, as far as the permitting goes, I certainly see a lot of off-grid systems go in without permits, but so it's just going to depend on each individual job. Certainly, building the system to code would be a good idea in case something happens or there's a fire. Then you can justify that you did the system the way it was supposed to be done.
Mm-hmm.
And of course, if it's in a place where it's going to be looked at, seen, you're probably going to have a permit to do that. And it theoretically, I think in most jurisdictions, an off-grid house is subject to the same code rules as a grid-tied house. I don't think the code doesn't really distinguish between the two, and there's certainly off-grid parts of the code.
Okay. And then do you happen to know what are the most common warranty claims?
Probably, well, either batteries or inverters. Yeah.
Okay.
Yeah, not a huge push either way.
Okay. We've got another one for remote locations. Do you recommend solar plus storage? What's the norm there?
Well, for remote locations, of course, if you're going to have solar, you are going to have storage. They're not separable. You can't really have just solar direct, and unless, I mean, there's a few circumstances, a few specific ways where if you have a solar direct, say to a well pump, where you don't have any storage. But for any residential type system or system where you're going to have any loads outside of when the sun's shining, you will have storage. Yeah.
Okay. We've got one more. When designing for off-grid residential, how does panel level rapid shutdown apply? And if so, how do you recommend achieving that?
Well, it applies just as much as it does to a grid tie system. There's really, the code does not distinguish between off-grid and grid tie for rapid shutdown. Although I see a lot of off-grid systems being put in without rapid shutdown, probably without a permit. Just because there are some installers who dislike it enough and it reduces the reliability or is seen to reduce the reliability of the system, which is critical in an off-grid system because that's your source of power for your house. So there is a push to sort of not put it in, but to meet code, it does have to be put in. And what you do for that, it depends on what inverter you have. Either the IMO Fire Raptor, which works with everything, but there are maybe easier or simpler solutions that work with the other inverters. Schneider now has a device that has a transmitter for the Tigo TS4Fs, and SolarArc works with almost all the different module level rapid shutdown systems. And I've got, if you run into an issue where you're trying to figure that out, I have lots of wiring diagrams of all the different ways of doing this for the various different inverters and charge controllers. And some definitely work better than others for this. And it is almost all module level rapid shutdown now. There used to be, systems where you would have string level rapid shutdown to meet the 2014 code. And those tended to be expensive and not the most reliable, and they've almost all disappeared. It's almost all these simpler, just module level rapid shutdown systems at this point.
Okay, perfect. It looks like those are all of our questions for now, but anyone who's still on the line, if anything, comes to mind afterwards, please feel free to reach out and we'll make sure. Oh, one more. Do we have a minute for another one?
Sure.
Okay. Battery sizing for larger loads. Example about how a battery capacity drops by hitting it with a large drawdown.
Well, yes, particularly with lead batteries, if you hit it with a large load, it will drop the voltage of the battery bank, and it does use the capacity faster. There's most of the batteries are rated at different discharge rates. So you've got 100-hour rate, 20-hour rate, 8-hour, 3-hour, or even they get down into minutes. And your overall battery capacity when they are discharged at a higher rate is smaller and it's fairly substantial. On the other hand, if you draw a large load from a battery bank for a short period of time and then stop and go back to a lower discharge rate, you will recover most of that capacity. It's all these chemical reactions going on in there. A lithium battery is different. A lithium battery will not really be affected much by the larger load, so long as you stay within the limit of what the battery can do. It really does not affect the capacity of the battery to charge it, to put larger loads or smaller loads on it. But the battery management system generally is limited in the amount of current that it can pass through. And if you pass that limit, the BMS may very well turn the battery off, which would not be really what you're looking for. So that's really the only limitation on the lithium batteries. You just have to stay within their limit, and if you do, it doesn't affect the battery capacity much. Yep.
Okay, perfect. Well, again, if anything comes up offline after we log off here, please feel free to reach out to us and we'll make sure to get any questions answered. And like Josh mentioned, the survey that'll pop up in a different window, anyone who provides us feedback on that will receive a PDF of this presentation today. So without any further ado, I think we can sign off and wish everybody a wonderful weekend. And thank you for joining us today for this wonderful presentation. And thank you, Brad, and thank you, Josh.
Thank you, everyone.
Yeah, appreciate it. Have a good weekend, everybody.
Thanks, everyone. Bye-bye.